in this lecture. Right. Yeah. Here I'm Kwante Kim, and I'm going to talk about today when time domain error circuits meet audio sensors in neuromorphic version in TinyML applications. So here is outline. I'm going to introduce what is neuromorphic audio sensor and why do we need a neuromorphic approach in that direction, in that implementation. And then I will talk about time domain audio feature extractor and then give a summary of it. So here is an example of voice-activated audio TinyML system, such as keyword spotting. This example is a keyword spotting, audio keyword spotting. So for example, if we say yes, then our voice signal is back to microphone interface, such as smartwatches or remote controls or power smart keyrings. And our voice signal is further processed by feature extractors to extract the frequency selected features as a feature map or feature vectors in audio frame. And those audio frames are further back to the neural network to select the most probable labels. For example, because we said yes, it should be yes at the highest label. So among the several stages of audio processing, for example, in keyword spotting chip, around 40%, actually almost half of the power consumption is solely allocated in feature extractor, extracting the features. And these kind of audio timing systems are very power constrained, such as it should be always on, consuming less than 100 microwatts in general, and latency should be less than 30 milliseconds to naturally interact between the users and the audio TinyML systems. And this latency number should include the feature extractor and the DNN classifier. And the dynamic range should be larger than 40 dB to cover a wide range of our voice signals, such as soft voice or very loud voice. And here is a brief roadmap of neuromorphic feature extractor. So in conventional feature extractor, we can see the microphone output is directly fed to analog to digital converter. But this ADC is very high sampling rate and very high resolution in general. And it is further processed by FFT plus triangular digital filter bank. And the output is audio feature frames, an audio feature vector that is generated in audio frames. On the other hand, in neuromorphic feature extractor, we bypass this ADC, which is power consuming, and it goes to analog bandpass filter, and the output of analog bandpass filter is going to spike generator or through rectifier and spike generator. And we can call option 1, option 2, and option 3. For neuromorphic feature extractor, option 2 and option 3 are corresponding to it. And if we want to interface neuromorphic feature extractor to synchronous DNN classifier, we need spike counters because these spike generators are fully asynchronous, and it should be synchronized with the specified spiking counting window. On the other hand, if we go to asynchronous spiking neural network, we don't need any kind of synchronization stage, such as spike counters. So here is one example of neuromorphic feature extractor that is morphing, that is mimicking, such as biological cochlea. The cochlea is located in our ear, and which is kind of a locate shape. And if we unload this cochlea, then we can find there is a planar shape, and that is called as a basilar membrane. And this basilar membrane has a base point and apex point. And according to the position of this basilar membrane, the different frequencies are different frequency of input amplitudes are stimulated in different places. For example, if we apply 6 kilohertz input, then the position more close to base point is stimulated. On the other hand, for 2 kilohertz, the position more close to apex is stimulated. Okay, then let's move on to rectifier and spike generator. In our ear, as we have seen in previous slide, we have cochlea and base and apex point. And also the output of cochlea is connected to inner hair cell. So this inner hair cell is generating spikes, which is the action potential shown here. This inner hair cell has a rectifying functionality. For example, in the positive directional traveling way, then inner hair cell generates more spikes on the other hand, in negative directional traveling rate, it generates less spikes, which is a half-wave rectifier here. And in this slide shows an example of high frequency plus low frequency mixed up as an input signal that it can filter out. And it generates high frequency channel and low frequency channel as more spikes. Okay, then I will go to motivation for neuromorphic approach. So here is a very vast survey of ADCs that is a state-of-the-art presented in top conferences such as ISSC and Precise Symposium from 1997 to 2022. So here x-axis has a speed and y-axis a figure of merit. So going to top right corner means better ADC. So if we look at the general purpose ADC in used in audio applications are having more than 20 kHz bandwidth. And even for state-of-the-art ISSC papers, such as presented in 2021, then SNDR performances like more than 100 dB, which corresponds to rather than 16-bit resolution. It consumes rather than 100 microwatt. And this power number is actually huge power for always-on TinyML systems. For example, Apple's AirTag or Galaxy SmartTag from Samsung Electronics. When it is operating by coin battery, and it cannot ensure rather than 1 year lifetime because of solely by ADC power. Okay, there is bandwidth ADC that we can get a 3 dB SNDR performance. However, this number didn't include decimal filter, which is a very essential building block for high resolution ADC, such as Delta Sigma architecture. And the second question I want to address is, what if we demand rather than 5 kHz bandwidth? Because 5 kHz bandwidth is specified the condition that our voice signals are mostly concentrated within 5 kHz bandwidth. So it can be possible sacrificing slight accuracy of the DNN classifier, but it can be still okay. But however, if we require rather than 5 kHz bandwidth, then we are having trouble, such as this kind of application. So there is a very high demand on audio TinyML in language evolution research. Here, example shows monkeys are interacting each other by sending signals such as P or food or tree calls, and we can see there is a spectrum. It touches across rather than 20 kHz, even touches 50 kHz. So for our language evolution research, such as this kind of monkey research, then rather than 20 kHz bandwidth is essential, and low power innovations are still required instead of just general purpose ADC. So that was one of the number one motivation of the neuromorphic approach. The second motivation is implementing the same functionality using analog versus digital circuits. For example, if we have seen that 40% power is located in feature extractor, and right slide shows option 1 and option 2 and option 3 for implementing the same functionality, which is MAC, multiply and accumulate operation. And we can see that there is a very steep slope in analog implementation, and it goes to it matches to it crosses the digital implementation in lower output SNR. So we can see that there are sweet spots that analog implementation can be superior over digital implementation, and which is more analog signal processing can be more efficient up to 8-bit precision. There was a second motivation. And the third motivation for neuromorphic approach is neural network acceleration. So for running a neural network and accelerating the neural network with higher energy efficiency or lower latency, in these days, in memory computing, researches are very emerging field, such as SRAMs or using memory registers. However, for implementing analog version of in-memory computing, around up to touching 70% of energy are solely allocated in ADC and DAC. So just data conversion energies are just wasted by 70%. So if we adopt asynchronous SNN instead of synchronous DNN, then we can save this energy waste and just eliminating this ADC and DAC, such as data conversion waste. And we can go fully asynchronous way of implementation, which is fully analog. No ADCs or DACs are required. And spike-based interfaces can be seamlessly integrated in asynchronous spiking neural networks. So I'm going to introduce the time domain feature extractor. So, okay, so we have seen the motivations of neuromorphic approach. Then here is an example of analog voltage domain feature extractor that has been adopted for implementing neuromorphic feature extractor. We have analog bandpass filter, rectifier, spike generator, and spike counter and DNN classifier. And this slide shows second order bandpass filter, which is based on source follow architecture. And if we further analyze this circuit in small signal model, then we can find the GM and 1 over SC, GM 1 over FC. This both of them are implementing integrator in S domain. Then we can find this is 2 integrator in a loop biquad. And actually, those best research and best survey are recently accepted for CAS magazine. So if you have interest to figure out more study about it, please check our archive preprint for further analysis. And okay, so this kind of source follow based second order bandpass filter is very power efficient and very compact because it's this single transistor implements just a GM cell for building integrator. However, this kind of voltage domain circuits are suffering from scaling unfriendly issue, which I will explain in later slides. So those source follow based filters were implemented in legacy process, such as 180 nanometer and 65 nanometer in prior works. So if it was kind of okay with it, but however, if we are facing the process technology nodes are scaling and advancing, such as from 315 nanometer to 16 nanometer or below, and the supply voltage is still scaling down and down, touching, of course, less than one volt. And this kind of situation, there is a signal swing loss because of supply voltage reduction, and headroom is a problem. And this goes to reduce the signal to noise ratio, and DC gain is reduced. The DC gain is GMR not. This means intrinsic gain of the transistor. If our DC gain is reduced, then it goes to nonlinearity and gain error of this kind of, for example, bandpass filter transfer function. And it's to mitigate to solve this issue, then we need large lengths in transistors. However, it goes to area and power penalties. So the basic question I wanted to answer was, is there any analog feature extractor that can benefit from technology scaling? And here is an example of answer that I can say yes. So if we adopt time domain feature extractor in analog circuit implementation, we can benefit from technology scaling. So here we have input PWM signal as a P-in with a fixed on time, and it switches on and off the ring oscillator in running faster or running lower. It switches on and off the current flowing into oscillator. Then it can represent the input on time with the average amount of oscillation frequency. Instead of using one oscillator, if we put 2 oscillators in parallel, if we extract the phase difference of 2 oscillators, then we can implement integrator in analog time domain integrator. Because there's delta T on is accumulating over time. This is because the phase domain output is actually integral amount of frequency. So these kind of oscillators are represented in S domain, and we can see that oscillator over S is transfer function, which is ideal integrator. And this means ring oscillator can be used as ideal face-to-face integrator. And it has infinite DC gain because it just go over and over, and it accumulates over and over as long as this oscillator is oscillating. And it doesn't suffer from signal swing loss, and it uses digital cells, which is the most important thing. That means it can benefit from technology scaling. Okay, so we built, we implemented ideal integrator. Then how can we build a filter based on this thing? This is just simple, basic, just feedback theory diagram with just one integrator and just feedback element. Then we can put one integrator, one feedback as analysis, and recalling the transfer function across the loop gain. Then we can find the A open loop gain over 1 plus beta open loop gain. And if we just analyze this circuit, then we can find it implements low pass filter in first order. Okay, then integrator can be replaced with our base domain oscillator, and the output can be extracted as a reference base, and the output is PWM signal, and input PWM signal can be also used. And it is scaling friendly first order low pass filter, and then I will explain how to implement in detail for each of building blocks. For subtracting time domain PWM signals, we can use just inverter for subtracting. So if we just put the inverter, then the polarity of input PWM signal is inverted. Then we can realize subtraction functionality. Then we can in the end, we can realize current mode add and subtraction. And for extracting the phase difference, we can put phase frequency detector, which is a very simple circuit with 2 P flip-flops and 1 NAND gate. Then here, for example, we can see the input phase difference is extracted as an output up and down signal. And here we are only using up signal for simplicity. In implementing differential circuit, we're gonna use down signal. Okay, based on this thing, in our listen circuit paper, ICC and JCC 2022, then we implemented a time domain second order bandpass filter with inherent rectification functionality. I'm gonna explain the rectification later. First of all, if we look at just this circuit as a hub, just divided as 2 sections, then you can find this is a pseudo differential circuit. We have oscillator plus PFD as implementing 1 integrator, oscillator PFD as implementing 1 integrator, means 2 integrator, 2 feedback. 1 feedback is inner feedback, the other feedback loop is outer feedback loop, which means bi-quad filter. And this is inherent rectification means. For PFD circuit, actually, this circuit has been widely used in PLL applications, phase lock group. And if we look at up and down signals, then we can find up signal is positive half-wave rectifier, which is very interesting, exactly the same as level activation function. And the other one, down signal, is negative half-wave rectifier. In conventional usage of this kind of PFD circuit, those 2 signals were subtracting each other to generate very linear input to output based relationship. However, if we add them together, up and down signals, then we can implement full wave rectifier, which is all digital design. And if we compare this PFD based on rectifier with voltage domain equivalent circuit, you can find that this is super simple and very efficient. Just needs 2 D flip-flops and 1 NAND gate. However, if we want to implement the same functionality in voltage domain, we're gonna need 3 OTAs, 2 bias currents, and so on, and active components and passive components. So we have seen analog bandpass filter and built-in rectifier in time domain, and the remaining parts, spike generator and counter, will be much more familiar with you. because I'm gonna talk about integral bio neuron. So here is a really basic building architecture in integral bio neuron that has been widely used in neuromorphic society. And we have input current and the membrane capacitor, the continuous time comparator, and the output of comparator is resetting our membrane potential. And the input current is increasing, then the output firing rate is also increasing, which is very popular. If we look at this integral bio neuron with relaxation oscillator, then it will be very interesting. This relaxation oscillator has been also very widely used in circuit society. And relaxation oscillator also has Laplace current and the capacitor, continuous time comparator, and reset switch. So what I want to say is integral bio neuron can be interpreted as a current-controlled relaxation oscillator. And regarding technology scaling, actually, this integral bio neuron is still voltage domain integral-based one. So it suffers from headroom issue because this transistor this transistor should be ensured with a sufficient VDS, and also the input current transistors also should be ensured with sufficient headroom for the voltage difference. And most of all, it uses static comparator, which is power consuming compared to dynamic comparator. And what about spike counter? If we count the number of spikes within fixed time windows, such as reset window, then we can interpret this counter as a frequency quantizer. And the integral bio neuron is actually current controlled oscillator. And if you are further interested, and then you can figure out and you can more study about this architecture as circuit papers. In circuit papers, you can find that this is actually CCO-based theta sigma modulator. So what I want to say is, if you put integral bio neuron with spike counter, you're actually building just analog to digital converter with the theta sigma architecture. So, okay, we have collected the required information about integral bio neuron and spike counter. Then we can actually build the oscillator using ring oscillator instead of integral bio neuron. The motivation for using ring oscillator is actually its base domain signal is very similar to integral bio neuron. This is base domain integral based one. And the base signal is always integrating, and when it touches 2-byte threshold, then it just fires, and the base signal is just reset to 0 and integrates again over time. And the most important thing I want to address is it doesn't require any kind of static comparator because it has an inherent 2-byte threshold, which is very nice advantage over integral bio neuron voltage domain design. So in our previous paper, we implemented PFM using ring oscillator and quantizer, which is 1-bit quantizer for the counting the number of spikes within time window, and it has an Extractor differentiator, and we oversampled the Extractor differentiator circuit, and the output is summated and estimated. So if you have interest and if you want to further study about it, please have a check our paper. So in our prototype chip was fabricated in TSMC 65 nanometer CMOS LP process, and we have an on-chip gain calibrator in our RNA accelerator side. We also implemented RNA accelerator to run the keyword spotting task. And its bandpass filters were 16 channel with 111 hertz to 10 kilohertz. Here is an example of audio signal response with the Google Speech command dataset. We applied GSCD keyword with yes signal with 254 millivolt peak to peak. Then we can find the yes part of yes signal has a low frequency response, and part of yes signal has a high frequency response. then it can be definitely helpful for analyzing and for interpreting the keyword at the RNN classifier stage. And here we also analyze the keyword spotting accuracy with computer metrics shown in left slide. Accuracy number was rather than 86% over 12 classes, such as silence, unknown, down, go, left, and so on. Okay, there have been very vast amount of papers that is studying this kind of audio signal processing chains. It was neuromorphic approaches and also non-neuromorphic approaches were there. Among them, actually, our work was the first oscillator-based time domain feature extractor that has been silicon verified with fabricated chip. If we look at the top power numbers only, then we can find analog counter power is much more power efficient than the other digital circuits, except for this paper, which is 340 nanowatts, which is very promising and very powerful low power number. However, this paper didn't include ADC functionality in their chip. So in the end, they're going to require ADC in system level, which means more power consuming in system level. And comparing analog voltage domain and analog time domain, our work didn't surpass the previous work's ultra low power consumption. However, I want to address several things. So first one is our one was verified with 12 class keyword spotting, and the other one was verified with 2 class voice activity detection. So VAD, voice activity detection, was meant for classifying whether this input speech is voiced or not. However, in our keyword spotting, it's more difficult because it should be also detect voice or non-voice, and also detect whether this voice is our predefined keyword or not. And the second one is we have a better technology scalable architecture. So if we implement the same functionality in the same process technology, then with the further advanced technology, then our performance will be much better. And this lastly, this prototype chip was the just first trial of time domain feature extractor. So many opportunities are left yet to be explored. So I'm going to give a summary of this talk. Neuromorphic audio feature extractor has a multi-channel bandpass filter-based architecture, and it has a rectifier and spike generator or PFM generator. And it can be either implemented using voltage, current, time domain circuits. And it is a promised alternative to conventional FFT-based processing because FFT-based processing has been studied very long time. And there are not much more room compared to our neuromorphic feature extractor side to be more studied. And it bypasses power-hungry ADC, and it has a better power efficiency up to 8-bit precision in general. And most of all, it can seamlessly interface with asynchronous spiking neural network, which is very also promising point. Not merely this bypassing ADC and better power efficiency up to 8-bit precision. Okay, lastly, I'm gonna give some examples of the opportunities that our time domain feature extractor can be used in other domain over beyond audio applications. This is one example of in-sensor processing area. So in this paper, ECG processing circuits were fabricated, and it has a cardiac health monitoring and biomedical authentication functionality, and it has ECG data as a digital input and the post-processing stages and the DNA classifier. However, this paper didn't include the on-chip ADC, which means our neuromorphic approach can be also effective. And you can see that the overall power breakdown at prior filtering stage is the most power consuming part, which means this is digital feature extractor side. And we can also benefit from our neuromorphic approach. And also there is some opportunities to to be connected with spiking neural network classifier. And the second one is brain-computer interface. This paper implemented ASSR-based ERE DPCI, brain-computer interface. This ASSR means audio steady-state response. So, for example, as shown in this slide, if we apply two stimulus with different analog frequency, with carrier frequency with 2.5 kilohertz, 1 kilohertz, and with the AM modulation with 43 hertz, with 37 hertz at left and right side. Then, according to our attention, in left side attention and right side attention, the output of EREG signal spectrum has a different peaks. For example, if we attend a more left stimulus, then the 37 hertz peak is more prevalent compared to right attention case, which can be used for classification to build a brain-computer interface. And this work implemented only the amplifier to ADC chain. So, and the feature extractor and classifiers were implemented in object in PC. So, which means we can also implement the neuromorphic feature extractor and the classifier. And lastly, there is a in-memory computing field, which is very emerging, of course. And this slide shows an example of 8-transistor SRAM-based in-memory computing architecture. We have read word line that is applying the number of pulses according to the input activation data. And this AT B cell is discharging the charge. And in the end, it is modulating the current amount that is discharging from capacitors. However, if we implement this capacitor versus ADC parts as an oscillator or PFD, then we can implement oscillator-based spiking neuron or PFD-based lateral activation function in time domain, which is also promising and very interesting. Okay, lastly, I want to give an acknowledgement of Sensors group members in any and financial support from funding agencies. So if you have interest for further doing the semester project or thesis, then please contact Bobby and Sichi for more study and research. And thank you for listening. So any questions? I'll be glad to answer.
So is the idea that you have a bunch of oscillators that are already you have a bunch of